In this video, I'll talk about the photon-induced transition probability. It can be vibrational transition, electronic transition, or any other types of transition induced by photons. I'll start with three questions. First, when the 1s electron in a hydrogen atom absorbs a photon with the right amount of energy, it jumps to one of the three 2p orbitals, but not the 2s orbital. Why? The infrared spectroscopy is a very useful technique in identifying functional groups in organic chemistry. But the IR spectra of the oxygen and nitrogen molecules are blank because these two molecules never absorb infrared photons. Why? Third question. A HCl, hydrogen chloride molecule, in the ground vibrational state can absorb an infrared photon and jump to the first excited vibrational state. It's called 0 to 1 transition. But really, it jumps to the second excited state, even if the photon provides enough energy. This is because the 0 to 2 vibrational excitation of a harmonic oscillator is strictly forbidden. HCl is not exactly a harmonic oscillator, but approximately we say it's close to a harmonic oscillator. Therefore, the 0 to 2 vibrational excitation of HCl molecules may occur, but rarely. Why? To answer these three questions, we need to have a solid understanding of quantum mechanics at the undergraduate level or even the first year graduate level, and then watch this YouTube video on solving the time-dependent Schrodinger equation, which is h psi equals I h bar times the first derivative of psi with respect to time. However, if you have not completed the physical chemistry series at the undergraduate level or taken any first year graduate level quantum mechanics, you may skip this video, but I want to mention this. At the end of the video, you can see that all photon-induced transitions can occur only if the following two conditions are satisfied. First, the energy of the photon must be close to the energy gap between the initial state and the final state of the system. What does that mean? If the energy of the photon is much larger or much smaller than the energy gap, the transition may not happen. The energy of the photon must be exactly same or very close to the energy gap. The second condition is this. The transition dipole moment of the system cannot be zero. The notation is mu from 0 to m with an arrow on top. Mu denotes the dipole moment of the system. From 0 to m denotes the ground state to the mth excited state. This arrow on top indicates this transition dipole moment from the ground state to the mth excited state is a vector. This m can be any positive integer. There's a formula for this transition dipole moment. Mu from 0 to m, it's this. It's a triple integral with respect to x, y, and z over the entire space. You may imagine we are integrating this function over the entire universe from negative infinity to positive infinity. This size 0 is the wave function of the ground state. Psi sub m is the wave function of the mth excited state. This asterisk is complex conjugate. So we're talking about the complex conjugate of the wave function of the mth excited state here and the wave function of the ground state. In the middle, we have this mu. Mu is the dipole moment of the system. For example, if you have a HCl molecule, then the dipole moment is pointing from chlorine to hydrogen. And it's a vector. Essentially, we need to compute the product of these three functions. The result is also a vector. And then we integrate this vector over the entire three-dimensional space. If the result is 0, we say the transition is forbidden. If this integral is non-zero, we say this transition, photon-induced transition, is going to be allowed. Now, what about a hydrogen atom? Does a hydrogen atom have a dipole moment? Yes. For a hydrogen atom, this mu is pointing from the electron to the hydrogen nucleus. What about the helium atom? Well, for the helium atom, you have 2 electrons, so you have 2 vectors, each from an electron to the nucleus, and then you can sum up 2 vectors by summing up their x components, y components, and z components separately. And then you get a transition dipole moment by integrating the helium ground state, excited state, and its dipole moment vector in the middle over the entire space. Without really watching the video, I want to show you the quantitative expression of the transition probability from the ground state, denoted by 0, to one of the many excited states, denoted by this positive integer m. M can be 1 or 2 or 3 or 4, etc. And this probability is this so-called wave function coefficients C sub m in front of the mth excited state squared. And to be more accurate, it's the squared modulus. So this coefficient can be a complex number. We need to take its modulus and then square it. What about the tau? Well, any transition takes time. So this tau is right after a time period of tau. What's the probability of finding the system in the mth excited state? The expression is very complicated. It's here. The derivation is even more complicated, again, in this YouTube video. But by looking at this, we realize there are 4 terms. 1, 2, 3 terms on top, and then 4, the 4th term on the bottom. So I'm going to explain this. This epsilon is the strength of the electric field of the photon. Remember, photons or light is an electromagnetic wave. So it's a combination of the electric and magnetic field. Over here, this is our transition dipole moment. Its integral expression is given here. It's a triple integral. And then this is just a sine function. Tau is the time period. So this means after this time period of tau, what's the probability of seeing the system in the excited state? Now, omega prime and omega. Omega is the angular frequency of the photon being absorbed by the system. What about this omega prime? If you multiply omega prime by h bar, so h bar times omega prime, that's the energy difference between the initial and final states of the system. So this omega prime is simply the energy gap between the initial and final states divided by h bar. Now what about the bottom? Again, h bar is simply the reduced Planck constant. It's h over 2 pi. Omega prime is the energy gap divided by h bar. Omega is the angular frequency of the photon. Omega is equal to 2 pi times the frequency. So if you look at this expression, it's the squared modulus of the combination of these four terms, right? So as long as this first three terms are non-zero, even if they are negative, we need to take the squared modulus of the product of the three terms divided by this bottom term. Therefore, regardless of their signs, as long as these three terms on top are all non-zero, we will observe a transition from the ground state 0 to the mth excited state. And also we know this. The electric field of the photon can never be zero, so this part is non-zero. This is the strength of the electric field of the photon. But this can be zero, this mu. This is the transition dipole moment from zeroth ground state to the mth excited state. If you look at this expression, if we have a zero mu, such as oxygen, nitrogen molecules with a zero dipole moment, and then this transition dipole moment is also zero. When that's the case, the transition probability is zero. The transition is forbidden. Finally, let's look at this term. You may wonder, this term is zero when omega equals omega prime. It's true, this sine function is indeed zero when omega is equal to omega prime. But at the same time, this bottom is also zero. So really, this sine function divided by this difference between omega and omega prime is simply tau over 2 by using the Taylor expansion of the sine function. So actually in this expression, this sine function divided by the difference between omega prime and omega reaches maximum when omega is equal to omega prime. The maximum value is tau over 2. What if this omega is quite different from omega prime? This sine function will be non-zero, but it's going to be between -1 and 1, a relatively small number. On the bottom, again, when omega is different from omega prime, they can differ by 10 to the power of 12 hertz. So basically, you're looking at a number between -1 and 1 divided by a huge number in order of 10 to the power of 12. And you know the result is going to be very small, and the transition is unlikely. All right, now let's look at this equation for the transition probability again on the next page. I want to emphasize that this mu is a vector. This epsilon is also a vector. In this mu, the transition dipole moment is a three-dimensional vector because of the three components of the dipole moment of the system. Which three? This mu, again, is the dipole moment of the system with x, y, and z components, denoted by mu sub x, mu sub y, and mu sub z. When mu sub x is 0, mu sub y is 0, and mu sub z is also 0, if you look at these three integrals, they will also be 0. And then we say this transition dipole moment vector is equal to 0. And then we say this 0 to mth transition is forbidden. Again, because O2 and N2 molecules have 0 dipole moment, no matter how they vibrate, it tells us their transition dipole moment is exactly 0. Therefore, they cannot absorb an infrared photon and undergo this vibrational transition. What about hydrogen molecules? Same reason, same result. What about CO2? This is tricky. A CO2 molecule has a 0 dipole moment in its ground state. But during asymmetric stretching of CO2, a non-zero dipole moment is produced. Just imagine there are two CO double bond. When one is shorter than the other, there is a non-zero dipole moment. Also, CO2 may bend. When a CO2 bends the two bonds, the bond angle is no longer 180 degrees. And then a non-zero dipole moment is produced. Because of this, the asymmetric stretching and the bending motion are both allowed. And that's why we can observe the infrared absorption of CO2 molecules. What about water molecules? Well, that's for sure. When water molecules stretches or bend, again, you will see the change of its dipole moment. Now we know if a molecule does not have a non-zero dipole moment and cannot generate a non-zero dipole moment during vibration, then its mu x, mu y, and mu z are always 0, and then the transition probability is exactly 0. What about electronic transitions? The excitations of electrons. Let's talk about the 1s to 2s transition of the electron in the hydrogen atom. So first, let's review some mathematical concepts. Even functions versus odd functions. What is an even function? Fx is an even function if this f of negative x is equal to f of positive x. So the value of the function remains unchanged when we change the sign of the variable. What's an odd function? Fx is an odd function if the function value of negative x is the opposite of the function value of positive x. Now let me give you a few examples. X squared is an even function, but x to the power of 3 is an odd function. X to the power 4 is an even function. X to the power 5 is an odd function. X is an odd function. Sin x is an odd function. Cosine x is an even function. And then there are simple rules. If you multiply two even functions, you get an even function. If you multiply two odd functions, you get an even function again. If you multiply an even function and an odd function, you get an odd function. And why is that? Well, you simply replace this even with plus 1, odd with negative 1, and you will see these four equations hold. Alright, let's review dipole moment. Dipole moment is an odd function of x or y or z. It depends on which component we're talking about. The x component of a dipole moment is an odd function of x, but at the same time it's an even function of y and z. So here's the statement. In mu sub y, the y component of the dipole moment is an odd function of y. The z component of the dipole moment, mu sub z, is an odd function of z, but an even function of x and y. Now, one more thing. The integral of any odd function over the entire space is exactly 0. Why is that? If you try to integrate an odd function from negative infinity to positive infinity, you will see the integral from negative infinity to 0 and the integral from 0 to positive infinity. They have the same magnitude, exactly same, but opposite signs. So these two integrals cancel. Therefore, the entire integral of any odd function over the entire space is exactly 0. And then we can tell if we have an integral like this, we just need to look at its three components in the x, y, and z direction. And if this function is an odd function, we get a 0 integral in the x direction. And if this function, the product of three functions, is also an odd function, we get another 0 in the y direction. And then finally, if this function, again a product of these three functions, is 0, and then we say this whole integral is the z component of the transition dipole moment in the z direction. Again, if all three are 0, we say the transition dipole moment is exactly 0. The transition is forbidden. So now let's look at one specific example. Let's look at this 1s to 2px transition in the hydrogen atom. Let's look at the x component here. So this mu sub x is the x component of the dipole moment. This 1s is an even function of x. This is because the 1s function is a function of r only, e to the power of negative r. When the sign of x changes, because r, the radius or the distance between the electron and the nucleus, is the square root of x squared plus y squared plus z squared. The change of the sign of x or y or z does not change the sign of r. Therefore, this 1s is an even function of x and y and z. However, this 2px is an odd function of x. Specifically, the wave function of 2px is x times e to the power of negative r over 2. The exponential function is an even function. However, there's an x in front of the exponential function. That makes this 2px an odd function. So really we have an odd function of x. This mu sub x is also an odd function of x. Odd times odd, we get even. And then this even times this 1s even function, the result is an even function. So we have an even function of x. And also, this product is an even function of y and z as well. Therefore, this triple integral is non-zero. When this triple integral is non-zero, we have a non-zero x component of the vector of the transition dipole moment, and therefore this transition dipole moment is non-zero. The transition is allowed. And if you want to try 1s to 2py transition, it may happen as well. But we do need to replace this mu sub x with mu sub y. And same for the z direction. What about 1s to 2s transition? It's not going to happen because 1s is an even function of x. 2s, imagine I replace this with 2s. 2s is also an even function. Alright, but in the middle you have an odd function. So it's going to be the product of even, odd, and even. The result is an odd function. And the integral of an odd function over the entire space is 0. Therefore, the transition dipole moment is 0 in the x direction. Similarly, it's 0 in the y and z directions. Therefore, the transition dipole moment is exactly 0 for the 1s to 2s transition. It's a forbidden transition. You will never observe the 1s to 2s transition if it's induced by a photon. On a side note, it's possible to heat up hydrogen atoms to observe the 1s to 2s transition. Alright, now get back to the vibration of HCl. HCl, although it's not an exact harmonic oscillator, but when the vibration is not too vigorous, we can use the harmonic oscillator approximation, and we can see the ground state wave function is an even function. The first excited state of this HCl vibration is an odd function. And then we have mu in the middle. The mu is an odd function. Therefore, the integral of an even function times an odd function times an odd function is non-zero. Again, even times odd is equal to even. So 0 to 1 vibrational transition is allowed. But 0 to 2 vibrational transition is forbidden because the ground state and the second excited states of the HCl vibration are both even functions. And then again, we have a mu in the middle. This mu is an odd function of x, y, or z. So if you examine the three components of the transition dipole moment, all of the three are exactly 0 for the 0 to 2 transition. Therefore, this transition is forbidden. Finally, in one sentence, if you need to decide if a photon-induced transition is allowed or forbidden, you just need to check if its dipole moment changes during the transition. If its dipole moment changes, then the transition is allowed. If it doesn't, then it's forbidden. Again, if we're talking about the stretching of CO2, the asymmetric stretching of CO2 changes its dipole moment and therefore is allowed. The symmetric stretching of CO2 does not change its dipole moment, therefore this vibrational transition is forbidden.